Hello, this is going to be part 6 of my sky watching series of videos. In the last one, I described how I thought of a different approach, and this video is going to explain how I went about doing that. So I had already found formulas online to calculate the sun's position and the star's position, but I didn't find anything that was reasonably accurate or reliable to calculate the moon's position. When I decided to go in this slightly different direction, I went and did another search, this time specifically for some Java code, and I found this particular set of code that this person has written. And the main thing that I was interested in was the core calculations required to determine the moon's local hour angle and declination. I saved a copy and I loaded it in one of my projects. And I had created this project for one of the other videos that I made earlier. And I decided I was going to enhance it by adding a bit of extra functionality for this purpose. And it was a temporary measure to see how well it was going to work. At some point, if I decide I want to make this into a slightly better project, clean the code up and make it presentable, I might consider moving it out into its own separate standalone application. So the main code involved calculating the Julian day and then using that in a whole series of other calculations that would essentially calculate a delta degree and alpha hour, etc. And then from there, I could use it to calculate the local altitude and azimuth. This method did not include taking an observer geocoordinate. So I essentially created my own functions to calculate the moon, the sun, and stars with the various parameters that I needed. When I started this was the method that I ended up creating. It was taken from there, as you can see. And I found out after a while that it wasn't as accurate as it could be. At one point in time, the moon's computed coordinates were in fact accurate. But as time would go on, the computed coordinates would tend to drift a little bit. And then at regular intervals, it would jump back to a new proper set of coordinates. So I would say that the error would extend as far as maybe 30 arc minutes, and then it would reset and go back to where it should have been. I wasn't really happy with the way it calculated the moon's position, so I found somebody else's source code, and as they indicated, there's always a trade-off between accuracy and computing time. So according to them, their particular library is reasonably accurate, but not exactly precise. And it does seem to have an accuracy of about a minute. And so I ended up replacing some of this code with the other guy's code and kind of tweaked it a little bit. I created a separate calculator to compute the sun's position, and that's based off of the NOAA Solar Calculator spreadsheet. And these are the columns in the spreadsheet. And then finally, one of the other spreadsheets that I had entered the formulas to calculate the stars' positions. I did something very similar. I can't remember where I got the original formulas from, but they're fairly straightforward. And so at this point, I had written a series of calculators that, given your latitude, your longitude, in this case, the star's right ascension and declination. In other words, this is your geocoordinate and this is the star's celestial coordinates along with the day and the time zone and the debug, which is not necessary if I were to redo this. Then it will calculate the local hour angle and the declination. All of these will calculate the local hour and local declination. This one takes the same set of arguments minus the star's coordinates. And here's for the moon. And so once I had the local hour angle and the declination for those objects, the next thing was to try to project it onto an image as if it was taken from a camera. The initial goal was to be able to locate on an image where the objects would be as if it was my camera. I tended to focus the initial computation and transformation coordinates based on that, and then the project ultimately took on a life of its own. Initially, this is the kind of view that I had generated. I assumed an azimuth of 180, or in this case, an azimuth of 0 for the North Star. The altitude I set to the difference between what would it be, the zenith and my latitude. So my latitude plus the altitude equals 90 degrees. The sun I made as a yellow dot, and the moon I made as a blue dot. Because at this time it's during the day, the sky is blue. I found a set of star charts that I used in another video earlier. And so I reused that to be able to calculate where the stars should be. If I wanted to change the view or change the day, I would go into a configuration file. This was at the start, change the numbers, then it might look something like this. So here I just changed the altitude slightly and change the date. Adding all the different functionality into some kind of configuration file and loading it on startup was not particularly efficient, but it was good enough at the start. So the next thing that I wanted to do was to make a user interface that let me change those values on the fly. I ended up getting rid of most of the configuration file, and I added a control panel. And next thing I knew, my control panel developed quite a bit of feature creep. So I'm going to leave this control panel aside for another video. But before anybody asks whether or not these equations are correct or not, whether or not it really is accurate, earlier today, I specified a series of geolocations, and I used SunCalc and MoonCalc to compare the values. So to give you an idea of how this would work, I'm just going to do SunCalc for my location, and you'll see in a second how that's going to work out. So while that's loading, I'm going to specify 44.7. This value doesn't matter. This is the object that I'm interested in. I'm interested in the sun, and I need to go to 1704. There we go. And so now if I go and pick my 45 and minus 75.6, 45.3, apply and go current time. So as you can see, SunCalc has the time of 5:04 p.m. There's 5:04 p.m. The altitude is minus 5.33. This is taken from the NOAA solar calculator, and it has minus 5.31. The azimuth is 243.1022, and this is 243.10. This is the current local right ascension and the current declination for the sun. And of course, this is the camera's altitude, azimuth, local right ascension, and current declination. I'm going to pause the video here, and I'm going to inject a whole bunch of stills that I've taken, but it's pretty much the same process. I pick a geolocation and a time here, and I pick the same geolocation and the same time here, and then you can compare these values here, altitude and azimuth, against these values here. So anyways, thank you for watching. I'm going to make another video. I think the next one is going to be where I showcase this a little bit more and show some of the functionality that I added. I think it's going to be rather interesting. If you like this video, don't forget to do the standard YouTube stuff. And I will see you again, hopefully, probably, maybe even later this week. So bye for now.